Alright, so before I do 16, the first thing I want to talk about is that right there. 3 miles, 30 degrees north of east. Like, what is that? So, let's talk about bearings. There's probably a good chance I probably taught this wrong a couple times in my life. So, let's do some funny things like 20 degrees east of north. That would be a 20-degree angle formed with north. So if I talk about 20 degrees east of north, the 20-degree angle is formed there. If I talk about something like 45 degrees south of west, all right, that's a 45-degree angle formed with the west axis. And most people know that one by heart, but the 45 degrees lies there. So the one that I'm looking at here is this 30 degrees north of east. That is a 30-degree angle formed with the east axis. If it was centered at the origin, you'd put your 30 degrees right there. So that's all very, very important. All right, so now let's go back to the question being asked. Draw a picture showing the man's path as a set of vectors. You won't need anything more than quadrant 1. Let's see, we're going 5 miles north, magnitude of 5. 3 miles at 30 degrees north of east. And by the way, this is the eastern axis. So we're going to put a 30-degree angle in there. And mine's not to scale. Now 4 miles southeast, if that was centered at the origin, that would look like that. That's pure southeast. 45, 45. But, by the way, that was what, 3? It's going to form a right angle to be 45 degrees. And God bless an interruption. I've been at this for 2 minutes. Be right there. It was Tristan bugging me. Let's see, that was 4 miles southeast. And lastly, 2 miles west. And that's pure west. So straight left for 2 miles. Anyways, there's your little diagram. Resolve each vector into components. I'm going to call them A, B, C, D respectively, just because it's easy. Vector A, and by the way, component form is change in X followed by change in Y. So vector A has no change in X, only change in Y. Vector B is going to take some work. I want you to remember that X is R cosines of theta and Y is R sines of theta. That's how I'm doing vector B. So without doing any math, the radius would be 3. It'd be 3 cosines of 30 degrees followed by 3 sines of 30 degrees. And that's what you look like without doing any math. You're supposed to know certain things, like you're supposed to know what the cosine of 30 degrees is, aren't you? I believe it's root 3 over 2. And the sine of 30 degrees is, I believe, a half. So if I do a little math here on vector B, I'd have 3 root 3 over 2. And then I would have 3 halves. What else we got? We got vector C. Now vector C, I drew a right angle. I did, but think about this one. Alright? Your actual rotation is 315 degrees. Now it's a little harder. You've got to realize that you have to think about how the angle would actually be drawn at the origin. So that's a little bit more difficult. So when I talk about vector C, I have a radius of 4 and I do the cosine of 315. And then I would also be talking about a radius of 4 and the sine of 315. one of these numbers has to be negative because the thing is falling, it's dropping, so it might be running to the right, which is positive as far as x is concerned, but it's falling, so the y component has to be negative, which is why we had to think about 315. So cosine of 315, that's over here. It's positive root 2 over 2. I don't know why that took me so long, but it's going to be 4 root 2 over 2, which is 2 root 2. And this one is sine of 315, which is 4 times the negative root 2 over 2, which is negative 2 root 2. So there's vector C. And the last one to go is vector D, which is what this guy right here is. Vector D simply runs left. It runs left 2 units and doesn't rise or fall anything. So 2 of those are super easy. Third one requires just a touch of trig. Find the vector showing the man's total displacement, which is the vector from where he started to where he ended up. So we'll call that vector E. And what they're asking for here, I can color code this a little bit for you, is they're asking for this vector right here. And I'm going to call it vector E. And vector E would be the sum of A, B, C, and D. That's all she is. So we're going to take all our x components, we're going to put them together. Vector A has an x component of 0. Vector B has an x component of 3 root 3 over 2. Vector C was 2 root 2. And then vector D was negative 2. Alright, we're also going to take all our y components and put them together. We had a 5 plus 3 halves plus a negative 2 root 2 plus 0. And we're going to put all this stuff together and get vector E. Let's do this up here. Now, nobody cares if you use irrational numbers. I mean, we're just going to do this without pushing buttons, okay? Vector E is going to be just the sum of those 3 pieces right there, which you really can't add together. I mean, I guess we could clean up the radicals or whatever, but that's what she is. We could make it look a little better. Let's think about that. 3 root 3 over 2 plus 2 root 2 minus 2. What we can do is we can give this guy a 2, make that a 4. We can give this guy a 2, make that a 4. And we can say it's 3 root 3 plus 4 root 2 minus 4, sitting pretty over 4. Alright, let's go with that, because why not? I really don't care if you use a decimal. But whatever. Alright, the y components here. I know I got a 5, that's cool. And I got a 3 halves. So that's going to be 13 halves minus 2 root 2. And again, I was doing 5 plus 3 halves. 5 times 2 is 10, plus 3 is 13. And if I wanted to look even a little prettier, at least mathematically speaking, I would put a 2 there and make that a 4. So 13 minus 4 root 2 over 2. And that is the vector showing complete displacement. Kind of funny looking, and you can use decimals. I'm not trying to throw you off. I just think you should be able to answer fractions. Add fractions. But forgive me, I'm not feeling 100%. How far is the man from where he started at the end of the walk? So what they're asking us to do here is they're asking us to find the magnitude. Find the magnitude of vector E. And magnitude is the square root of x squared plus y squared. That's all she is. So these big fugly things I've got, I'm going to have to do some work. As much as I care to want to do that by hand, I just don't have the time to do it. So I'm going to do some button pushings. Alrighty. So what am I going to do here? I'm going to do the square root math num n over d. I need a set of parentheses there, don't I? I got a 3 root 3 plus 4 root 2 minus a 4, sitting pretty over a 4, and that quantity is going to be squared. And I got to add in the other thing, so plus parentheses math num n over d. That one's 13 minus 4 root 2. So pretty over 2 squared. There we go. It's a little over 4, about 4.052. So the magnitude of vector E is about 4.052. And this would be miles, by the way. Which, you know, he walked 5, 8, 12, 14 miles. He could have just walked right through the trees. But maybe there was a ditch or something in the way. I don't know. It doesn't have to make any sense, but there was probably something in his way. Alright, now we're on the easy peasy things. To parameterize a curve, you either let x or y equal t. That's all you do, nothing more. Alright. Now, you will have to resolve for the other variable. Because, you know, when you type these into y equals on a TID4, it says x of t is. Now, that's the goal. You have to have an equation that says x of t equals, or y sub t equals. Now, it'd be really simple to let this one, let x be t. And that's a choice. So let's do if we let x equal t. Alright, that's cool. Now the second equation would become t equals y squared minus 3. And we would have to resolve for y. So if I resolve for y, I'd have t plus 3 equals y squared. And I would take square roots. Y would be technically plus or minus the square root, which I can't type out on this thing, of t plus 3. Nothing wrong with that. Or I could let y be t. Alright. If I do that, I'd have a pretty simple equation here. I'd have x of t, using substitution since y is t, is t squared minus 3. Now what I'm trying to tell you is think before you math. One of those was easier to do than the other, wasn't it? And a lot of times you'll find that it makes sense to plug in here. It makes sense to let the variable where powers are being done upon to become the t. But think before you math, kids. That's all I'm asking you to do. Rewrite as a Cartesian equation. So a Cartesian equation is we solve for y. That's all we do. We solve for y. That's what we have to do. So the idea here is to solve for y and then substitute. Let me rephrase what I'm saying here. We need an equation where y is written in terms of x, because we're thinking about y equals mx plus b, stuff like that. Y equals, variables called x. So what I'm going to have to do here to get that situation written up is I'm going to have to solve the first equation for t. So I would say x minus 1 equals t to the third power. Then I would take the cubic root of both sides. I'm going to do that using exponents. And now that I've done that, I can turn around and I can plug that result into the next one. I know what t is. I can put it there and I can put it there. And I can have something I could actually go to y equals and graph. So everywhere I see a t, I'm an x minus a 1 to the 1/3 power. And what do we have here? Minus sine of, I'm going to use a double set of parentheses here because I need to include that 1/3 power. And I have something I graph. And I'm just going to show you, whenever you convert to a Cartesian, you usually gain some extra crap that's not there. That has to do with this. You know, this is a cyclic function, cycles between 0 and 1, right? So there's some stuff that shows up that's just kind of introduced. But at least half the graph will look the same. So what's the original equation look like? Let me put my thing in parametric mode here. And the original thing was x of t is t cubed plus 1. And then we had y being t minus the sine of t. And we'll just do a zoom 6 like I've trained you year after year after year. This is what you get. It's not anything special. It's just kind of a curve that starts there. We can play with the window. We can look out a while. Change the x max to be 100. Yeah, I don't know if you ever looked at the window on the t-scale. There's different things like t-min 0, t-max 360. I must be in degree mode. Yeah, I am. I need to be in radian mode. If I look at I don't want to look at 100 units. Let's go back to zoom 6. I just see that, right? Almost looks like a straight line. There's a little bit of curve. I think if you zoomed in on it far enough, you'd start seeing the cyclic nature of sine. It should go up and down a little bit. Yeah, maybe you can see the little bit of a wave it's doing. I don't know if you can or not on your end. You'd have to graph it to probably your calculator and hold it and look real close. But it should be going up a little bit and it should be going down a little bit. Up a little bit and going down a little bit. I'm mainly just being curious here. Well, that looks even worse, doesn't it? Anyways, let's take a look at the function I wrote. I said that it is equivalent to x minus 1 to the 1/3 power. Take away the sin. I got a double set of parentheses there because I wanted to keep that exponent inside the sine function. I'll just do a zoom 6. And we're probably going to have some stuff show up on the left-hand side of the graph. Yeah, that stuff right there. Maybe you can kind of see it's trying to curve a little bit too, like a trig function would. It's not perfectly straight. And yeah, they're the same thing. But this stuff got introduced. That's probably should have had a domain restriction put in place. Anyways, that should be your entire, no crap, there's one more. All right, I think I got enough voice to do it. This one's easy. We did one of these in class in your notes last time we did notes. But the idea here was that if we take x equals 2 cosines of theta, I can simply divide both sides by 2. So I know that x over 2 is the cosine of theta. And I can do the same thing here. Y over 3 is the sine of theta. And you know, there's an identity out there that we just push and push and push and push and push, and it comes into play here. I know that sine squared plus cosine squared is 1, and I know sine and I know cosine, so why won't I just put them in? I'm going to swap the order here. I'm going to put x's first. I have x over 2 squared plus y over 2 squared must equal 1. That'll give me x squared over 4 plus y squared over 4 must be 1. And what you're actually drawing here is a circle, because I could 4 everything. And I'd have x squared plus y squared equals 4. So what you got is you got a circle centered at the origin, the origin with a radius of 2. And that, oh, I'm wrong. That's a 3, isn't it? That's a 9. Oh, fudge. You wouldn't 4 everything, you'd 36 everything. I'm sorry, what you have here is you have an ellipse. This thing goes out 2 units on the x-axis, left and right, and it goes out 3 units on the y-axis, up and down. I'm probably going to teach all ellipses, because I've got some kids who are planning on going engineering, so I'm probably going to teach ellipses. That's an ellipse. So there is that one. I'll teach ellipses after your challenge exam on May 2nd.